people say, yeah, so I understand if the government then there's it's a huge data, so you want to build some server farm, but for the director, people like I mean, we're very sensitive to natural products agriculture. He works very I'm scratching the surface of the surface. So I'm going to push it. I'm trying to tell myself the expert. I don't believe that there's one so remember when he took those jobs in the basement? Oh, yeah. The cloud can you get somewhere? That's really hard. It is unbelievable. Well, against whatever they all things that were in big companies that deal with fire.
No, I'm just thinking, well, we had this everything. You guys have iRobot vacuum? They're much more about it. I work for Grace, a German company, and they came over and it was in Conshohocken, and they said, oh yeah, you can't have a female salesperson in Italy, they'll just ignore her. You know,
that's what I'm going to do now. I'm going to scare my kids.
It doesn't quite have the momentum that's hard to
you can get mad. What? Say, oh, blah, blah, blah. But now even if you're going to be a business person, you have to say,
that's in my last and my wife told me
I can try
if you want, I love that possibility with no I'm going to tell you 1 hour after, he said my life. Boom. Oh, boy free.
I know
every
say that
not so bad.
they treat differently than they do for women in their own. I mean, a lot of times
they can use
you need a strategy you need to be aware of.
Because now I'm using a certain now. Why not? I'm using now because I said this unstated interest.
So how are we doing?
Yes. Yes.
Well, I'm going to go with the cereal. No, there's a lot of places that I think I could ask questions. One of the things that if I'm not familiar with where they're asking me,
Do you want the intro on the live stream or not? I thought you did. I'll do whatever you want.
I need to make sure that I'm going to feel safe.
I'm going to keep my remarks brief. If that's what you want, that's fine. Okay, let's wait 2 minutes.
After me is me. So I need to take over.
I can teach you.
Want to give a talk at CCN? We live pretty far away, so. That's an area that you see an awful lot of.
Our fall schedule's not open right now, so.
Personal care now. A ton of jobs.
Right.
Send your contact.
And
So that's where a lot of value in the industry is.
Oh, give us a card, right?
The book model.
It's definitely a lot that
Yeah,
I give
right.
someone else.
Right.
You know,
I just don't want to make you drive all the way.
several fold.
Orchards.
That's another one like that, where if you don't have your background, it's hard to break in.
We were trying to have meetings.
I mean, even if you're a formulator and you've developed products in other areas, it's hard to get into personal care.
Oh, up there, yeah.
Is that true?
Yeah, well, it's like pharma. There's like, if you don't have that pharma in your background, you apply. If you want to, that was a hard lesson I learned when we moved here from Chicago. Because I was like in the middle of America. Johnson and Johnson across the street and down the street, but they weren't down then, they were Roman Haas. I have Teva, I have all this pharma stuff right where I am. And I went narcissist because I was coding sealants, elastomers, I was, you know, that, I didn't realize what a hard line it was between that type of chemistry and pharma.
Specialist in dieting with the MPOX, and they see some.
Like when I did biocides, there was a list of chemicals that you
modified
could
data and
use for
transferred
biocides.
data
You weren't
from
allowed,
one
I mean,
department, second.
we had a list that was called the previously used in pesticide formulation list. And it had like precedence and accepted. And if you tried, I had a good phone.
Yeah, because I think it's sort of separate.
That was,
so.
and they made me completely reformulate the whole thing and got all the tests all over again because it was less than 100%. Yeah.
So, you know, I have a lot about quantum and I didn't, nobody explained what is quantum.
My politician.
What is it like? It's a beam based on a beam?
So it has to do with, you know, if you reduce things to seven, reduce what?
No, I understand. But how you reduce one to zero?
You know what? I'm just going to get everything around the table. I forgot. Don't put this on. Let's just introduce themselves. And later on, I'll introduce the CCN January. We're ready to go now.
So small.
3 minutes. All right.
It's kind of
So you'll sit down.
what they call like
They were talking about
Yeah, so pretty model.
around page 7, plus or minus, whatever. And he says,
Now, we'll
gosh,
it's 2 minutes early.
it was hard for some reason. You're like,
yeah, from Apollo 11.
We're going to start.
56 megabytes.
Do you want me to?
it's a high school chemistry. Why are she?
The process of Apollo 11 equal to the one
Might be
where
around
we
in a
actually if you have a new one.
Hello. Good evening, everybody. Welcome to the January 2019 meeting of the Chemical Consultants Network. I'm Keith Wing. I'm the incoming chair of the Chemical Consultants Network. We're fortunate enough to have other past chairs sitting with us, Dr. John Newport and Dr. Roman Bielski. I wanted to mention that the Chemical Consultants Network is a topical group of the American Chemical Society Philadelphia section. We're also fortunate to have Mr. Joe Martino, who's the chair-elect of the ACS Philly section here with us. And we also have a number of experienced consultants here, as well as newcomers, glad everybody's having a good time and can network. We have today two very, very wonderful speakers. Dr. John Newport, again, our previous chair, and Dr. Peter Joyce. John is with his own consulting company, Chemventive, and Dr. Peter Joyce is with his own consulting company as well. They're going to be talking about two different topics. One will be resources that are current and being updated that chemical consultants can take advantage of to further their business, as well as an interesting topic technically, which is flow reactors, and Dr. Peter Joyce will update us on that. And with that, I'm going to bring Dr. Roman Bielski up to introduce our two fine speakers.
Thank you. I know both gentlemen who will talk tonight very well. I work with both of them. I have worked with both of them. Let me start with John Newport. He will talk about resources. He has this talk already some time ago, not once, but more. So you can find online some of the elder information. Today, John will talk about new things which are worth discussing. I know John for so many years I can't remember, but I can tell you he did his PhD in Manchester in England. He's a polymer chemist and he worked in all his professional life he spent in the States, mainly in Hercules, but in some other companies. And after he retired, he started to become a consultant, and I work with him often. He's theoretically a polymer chemist. He's more than a chemist. He's exceptionally talented and creative person who can work in any area. If you ask him about becoming a geologist, he will become one, and he will be a wonderful one. John consulted in any area of chemistry with emphasis on polymers. And you will learn a lot from John, and if you want to learn something about performing chemistry, John is the right person to ask. And let me give you a few more words about Peter Joyce, who I met, I can't remember when it was, 18 years ago. And we worked for some time. Peter is a chemical engineer with MBA from Berkeley, and he worked for 30-something years in the chemical industry in various areas, fragrances and flavors. And then when I met him, he just started a company which tried to use phase transfer catalyst to environmental problems. And then we switched to removing methyl bromide from fumigations. And John and Peter did fantastic things in this area. But now he is involved in this revolutionary methodology of performing chemical reactions. And Peter will tell us much more about it. Thank you.
This thing will work. It's been asleep like a lot of us.
No, it's off.
Whoops.
There it is, John.
We got it.
Where did it go? Bear with me a moment.
Can you do
Well, good evening, everyone. Thank you for being patient while I was getting that organized. I've given a talk on resources for consultants about 4 or 5 times over the years, and the last time was about 5 years ago. as Roman said, the summary of that is on the website, and the idea was basically to have a list of useful resources for everybody to use that were low cost or free. And let's move to the next. What happened there? Yeah, please, let's go. That's the one that should be showing. Maybe it's not. Oh, I see. It's not on. The slideshow. What's happened? We can go that way if you like. We can go down. It should be going. It should be working.
What's the problem?
It's not projecting what's showing on the screen. So.
It's not projecting. Okay, 1 second. I think that. Can I take it?
Mm-hmm. Mm-hmm.
Okay, there. Now we have to make it the slideshow. Yeah, that's it. Okay, now
It's working.
Now page down. Okay, there we go.
There we
Okay,
go.
thank you. Thank you.
It's a good resource. Let's write his name down. Anyway, I promised only to talk for 10 minutes. And all I want to do is to give you a brief update that covers some of the changes, because as time goes by, websites come and websites go. I want to talk briefly about a couple of new sites that I found interesting, but mostly I want to request input from everybody here and anybody else who is listening to the live stream for any sites, any databases, any information that they have found useful while they're working as a consultant. And I will take any of that input and integrate it into the revised version. If we could go to the next slide. So basically the topics that have been covered are listed down here, and you'd find those on our current website. And the ones that are highlighted in red are just the ones I'm going to say a couple of words about. We can go to the next one. One of the main challenges for any consultant is to find work. And of course the most important way is through networking. But you will also find that there are a number of other opportunities that you can have by going to some of the open innovation platforms, such as 9 Sigma, Sentinel. I take it that everybody's familiar with these companies, and I've used actually most of the ones that are showing up here. But there are some new ones that weren't listed previously. This one here called InnoGet. It publishes both challenges as well as if you have a business that you want to start, you can list with them, and you can get investments that will help you do that. Idea Connection will allow you to, excuse me, both join teams to solve challenges, as well as recently what they have done is to give you a list of individual companies that also will just put out on their websites things that they're interested in, things that they'd like people to work on for them or with them. And it's convenient to have a consolidated version of that. Some of the current big challenges that you will find, there's one that's just recently shown up for kidney dialysis, which is actually a wonderful engineering problem. You've got solution A on one side of a membrane, solution B on the other side, and you're interested in transferring contaminants from one side to the other so you can flush them away. This one has a prize of like they'll be awarding 6 prizes of $75,000 apiece for people who can help improve the state of kidney dialysis, which is actually a major problem. It takes about 4 to 6 hours a week, a time rather, and you have to go in for about 3 to 4 times a week. So it's a very disruptive process for anybody who is in stage 4 of renal failure. And so it's actually a good challenge for chemical engineers and chemists, and Roman and I are working on this. We would very much like to win one of those. There's one on improving the efficiency of air conditioners that's worth about $500,000. Now, mostly the challenges that you'll find listed are more in the $10,000 to $30,000 range, and probably 3 or 4 of them in this last year, I think. Let's go to the next slide. Even if you're not interested in doing any of the particular challenges that you'll find listed on these open innovation websites, they do reveal some of the things that people are interested in. You may find that an award that's offered doesn't seem to you to be anywhere near what the technology would be worth. Maybe you want to develop it yourself, and Roman and I have actually tried to do that in one instance. Also, things that are being advertised could be of interest to a client. And I've come across that. I picked up a client here actually about 4 or 5 months ago. And the company that he is with is basically, well, I won't go into the details of what they do, but at least there have been several recent challenges where their technology could be used to solve it. So I've been able to introduce that client to those opportunities, and we're working to see if we can improve things. Let's go to the next slide. The only thing I wanted to point out here is that we had a talk in October, a joint talk, where we cover strategic alliances, and as part of the live streaming that we've started, this talk is now available for anybody to see whenever they want. Let's go to the next slide. This just shows you that the things that you used to find useful have now disappeared because presumably somebody was not maintaining that website. Let's go to the next slide. Some of the databases that had some useful information have disappeared. They're the ones in red. Let's go to the next one. But there's a couple of sites that I've used recently that I hadn't run across before, which actually has this one here has a wealth of information on chemical compounds that rivals ChemSpider, which is also another workhorse of the industry. Let's go to the next one. And NIST has a tremendous amount of information on thermodynamics, which I only came across recently. I don't know if other people have used that or not yet, but these things are actually very, very useful. Let's go to the next one. This lists a few other databases that we've found recently. This particular one here, Roman pointed out to me in a recent challenge that we took care of. And this is the sort of thing that I'm very interested in. If anybody else has any access or any links to any databases of properties, which would be very handy for us all to look at. Go to the next one. Again, this points out that we had a great talk in September by Chris Owens, also of CCN, on basically all the things that you would need to do to become a consultant or an entrepreneur. And as we go on through our live stream connection, we hope to have a whole series of useful resources for people starting out as consultants to refer back to. And I think that's basically all I had to say. Yeah, that's it. So, as I said, a plea from me is, what have you found useful? Would you please email me some links? And I'll be sure to incorporate it so that we have a broader document for us all to benefit from. Thank you.
Now we'd like to welcome Dr. Peter Joyce to the stage.
Thank you, John.
Oh, we're going to have to...
Oh, it's a separate slide. Jack?
Go to the other.
It's another file.
Another file.
It's the second slide.
Just the second one. Let's go up here.
There we go.
Here we are.
Great. Thank you. Put that back up.
Okay.
Back to the first page up.
Yeah.
Great. Well, thank you everybody for inviting me to give this talk. I really appreciate the opportunity. I've known several of you for a long time, and John I've worked with over the years, and certainly Roman. Roman hasn't talked about his other major attribute, and that's his humor. So if you want to get to know Roman and get some humor you've never heard before, you'll really enjoy it. But anyway, what I'm going to talk to you tonight is about his flow chemistry, a relatively new phenomenon that's been out there for about 10 or 15 years that is growing steadily. The nature of this talk is an overview. It's not a detailed analysis of any one chemistry or any one reactor design, what have you. It's to introduce you to the broad spectrum of what's available. And I'm going to scratch the surface of the surface, because there's a lot of depth here. And there are things that you may see up here that, well, he didn't talk about, must not be available. If you can think of it, there's someone out there that wants to develop the equipment, the technology, and the techniques in order to make processes continuous. Next slide. And getting started on this, I was very enthused by looking at an article that came out Monday from a manufacturing chemist in the UK about the LMAP group going heavily into continuous technology. And there are several other reviews like this that I've got in my, that I'll hand out at the end of the talk to show you the general introduction and the production capabilities that are already happening within the pharma industry. But if you look at this paragraph at the bottom, I call your attention to that. It offers, continuous processing offers significant improvements in relation to product quality, process safety, reduction in plant footprint, and provides the ability to perform chemistry that is difficult or impossible to do in a batch mode. So what this world is I've been a chemical engineer for 35 years and developed a continuous polypropylene process, and it's always a better way to go because the thermodynamics of a continuous process are very easy to manage. However, back in those days, we always thought we had to run for 8,000 hours and run in 4-inch lines and only apply to the oil industry. Well, that's not true anymore. There are people out there doing continuous processing, making kilo batches, 4 or 5 kilos at a time, continuously over 3, 4, or 5 days, highly valued intermediates, and making money doing the same time. You don't have that concern. All right, next slide. All right, so I'm going to start with a very simple comparison for, and this is just one attribute of continuous processing, but this elucidates some of the advantages of the overall process. Next. So if I look at the 10 cc reactor volume, the surface area to volume ratio in a volumetric flask, which is what I've seen Roman do a million times, is 1.8 units. So that's the surface area divided by the volume. In a coiled reactor, which is a long flow tube of the same volume, the surface area to volume ratio is more than an order of magnitude greater. Next. So if I'm looking at an exothermic reaction, I'm a chemical engineer, the basic equation is the heat release from every reaction is the heat transfer coefficient times the surface area times the difference in temperature. Well, I'm just showing you that in the same reaction, the amount of the area has gone up by an order of magnitude. In a flow system versus a batch, which has got a stir associated with it, you're going to have a much higher heat transfer coefficient also. In fact, I'm going to show you some systems a little bit later on the top of that heat transfer coefficient skyrockets. So if I've got the same heat of release, then U and A are going way up. What happens is the need for the delta T, next hit the page down, delta T plummets. So what does that mean? That means that reactions that you might be running cryogenically at minus 40 or minus 50 degrees C with dropwise addition in order to quote unquote get the heat out, you don't have that restriction anymore by using the flow system. You could have a delta T on the order of 3 or 4 degrees C for your heat transfer fluid, and reactions that you might run normally cryogenically can be done at room temperature. And I'm going to show you an example of that later on also. That's just one attribute of a continuous system. Okay, next. So what is flow? This is tube chemistry. This is my interpretation of it. You've got a pump that's pumping reagents through either a coil, which is here, which is a wrap. I should have brought one with me, I didn't, but a wrap coil of tubing that's usually 1/16 of an inch in diameter around a mandrel for heat transfer, or going through a chip. I'm going to take this chip out here that I brought with me. I know this is video, but just want to show this is a static mixing chip with microchannels in it. This is 1.6 ml chip. This is worth several $1,000s, so kind of keep track of it. And also, the last type of reactor is a packed column, where you can, if you do want to do hydrogenation, do palladium and carbon reaction, and then for your product collection. So that's a simplistic overview. Next slide. So where are we with all this? Well, the equipment selection for reactor technology is based on the exotherm on the y-axis and the residence time on the x-axis. And if you look at all this, the world we're in right now is batch and CSTRs where fairly long reaction times and fairly low heat release. If we go back up this curve where we have really high exotherms and we want to do these reactions, and some reactions are over in milliseconds and quarter-seconds, you need microreactors or spinning disk reactors. And many reactions fall into the band of this exotherm of heat release versus time. So that gives you a general idea of the nature of these reactors and what their capability is. Next. So reactor types and strategies. Next. Flow tube, which is a straightforward tube, just giving you residence time, but it's for homogeneous reactions, non-precipitating. It's very good for reaction screening and very, very low pressure drop. Next. Microchannel reactor, which is similar to this chip, but these come in much larger scales that I'll get into a little bit later that can make tons of material per day. They have a direct scale-up path, extremely high mixing because this chip, you can't see it, but there are interstitial microstatic mixers within these channels. And so the flow path is extremely long, very, very narrow chip. John, if you take a look at it, you can pass that around if you will. So very, very narrow channels for an excellent heat transfer. But also, again, both of these for non-precipitating reactions because there's solids that plug them up. Next. There's another type of reactor we'll talk about, which is an external agitated reactor. External means that the reactor itself is being agitated externally. There's no drive shaft. And I have an example of that here also, which I'll hold up. This bad boy is a little heavy. And we'll get into this in a little bit. And this whole reactor shakes. And there are interstitial CST, this is the analogous to CSTRs in series. So this gives you plug flow through the reactor at very, very low throughput with high heat transfer as well. And this is good for slurry reactions. And next, spinning disk reactor. Really extremely high shear mixing, very high exothermic reactions at short residence time. These are all available out there and are being developed in developing articles that are some are being published obviously, but some of this is being done at pretty high levels within the current pharmaceutical companies. Okay, thanks. So, what's out there in the literature? Well, production of Z-ethyl 2-cyano-3-phenylacrylate. I'll leave it up to Roland to explain this chemistry because I won't be able to do that for you. But in essence, the basis is the fact that you can scale this up by a factor of 7,300 to make this final product. And what this shows is the small chip that I just showed you now on a much larger scale with all the microchannels fitting into a series of plates. And those series of plates, in essence, can be stacked one on top of another so that one set of plates can talk to another, so you can just keep adding those on. So in essence, you can have microchannels of a very small scale, same resonance times, same Reynolds numbers of what you do on a very small scale in the lab, and just blow that up in order to make very large production volumes. And this is making 89.3 grams of this at very high yield upon precipitation. And the company that does this is Chemtrix. Next. So what this allows you to do, as I mentioned before, is it allows you to then take this from a very small scale, these are syringe type pumps here feeding into a small chip reactor, develop your technology at a very small scale, and then go immediately to the next large scale and then very large scale all at the same time. So in essence, flow chemistry is not something that's an idiosyncrasy or something that's being thought about. People are actually doing this and doing it at production volumes. Next. And then this shows the same plate and frame reactor design for a very large scale, where the first plate might be a mixer, 3 or 4 plates in a row for resonance time, and then a quench at the end in order to handle your chemistry. Let's stop for 1 second. The CEO of this company, named Charlotte Wiles, she probably is responsible for the discontinuity in this field, in that her PhD thesis in 2000 to 2004 timeframe showed that the flows, pressures, and temperatures could be possible in order to affect small-scale reactions and also scale them up. And that's something I encourage you to look up because it's a brilliant piece of work. Next. All right, so this shows again, the chip reactors, small scale of microchannels. I've already gone through that, and these static glass mixers. And what people are realizing is it can stand up to 40 atmospheres of pressures, temperatures up to 260 degrees C. Next. These are core reactors of various sizes and shapes, whatever resonance time or volumes that you want, and also packed column reactors for hydrogenation. Next. These overall units are then put into a robot. The robot, in essence, will allow you to do multiple experiments at the same time through a fraction collector. So what the chemist can do is he can sit there and decide, okay, I want these reagent ratios, these temperatures, and these pressures. I'm going to dial that in using this keypad here and determine that I want to do 10 different experiments, run those experiments, and then take the reaction products from those experiments and put it into a fraction collector, collect small vials of that, put a cap on it, boom, it goes right into your HPLC or GC or GCMS or whatever you want. You can have 10 experiments done in the morning and have them analyzed in the afternoon. So this is very rapid screening for a broad range of experiments based on different ratios.
What would a setup like that cost, Peter?
This unit is about $50,000. I've got one in my car if you want to.
Oh, good.
Yeah, okay. And also a fraction collector on top of that. And the fraction collector is a slave to this unit. One thing is that all this tubing is here. These are high pressure pumps and reagent and the coils and what have you. All of this is well thought out and it's integrated and it works. Go ahead, next. So one of the things I just want to bring out about this is one attribute of this is that when you flow reactants through a tube, they're going to disperse in both directions, both in the feed forward and also lagging back. So if the reagents you've committed to the reaction are a volume of A and B, and you were looking for that volume at the end, you can dial in an attribute called pre-collect and post-collect, that if this is very valuable material to you, you can collect absolutely all of it and make sure that you collect everything that's on that takes into consideration the dispersion. Next slide. However, if you're not interested in collecting everything, but you want to know the maximum concentration of your continuous reaction, you can put negative values in for the pre and post collect and just collect the heart of the peak. So in essence, that tells you the actual maximum concentration that you got from your reaction. And I'll argue that in batch reactions, a lot of people don't realize this because they've got a lot of back mixing, and in essence, they destroy the concentration gradients, whereas that doesn't happen in these continuous systems. So in essence, you might be getting yields at 20 or 30% higher just by not going through this exercise. So if you take this and suppose this is your final scaled up reaction, and you use a huge volume of A and B, then you know the conditions are right for giving you the maximum material that you can collect. Next. Other things I want to mention is that one of the recent things that's available are a photochemical reactor. This particular one produces 700 watts of power at 300 volts DC, 450 nanometers wavelength. This is very popular and also can be made into a range of 330 to 550 nanometers. It's connected to a cooling unit because the unit produces a lot of heat, and it can be scaled up with a larger reactor coil power. Next. Another unit operation is a flow UV, which is in essence measuring in situ UV wavelengths up to 5 at the same time, and also showing that on the computer, so you can in essence see your reaction in situ as you change conditions or what have you, and see what products or byproducts you're making on the fly. And finally, in that scheme of things, this is very interesting here. This is a gas addition module. Suppose you want to do a hydrogenation, and how do you feed hydrogen into a high pressure reactor? That's not something people usually do. They usually put it through a trickle bed and let it stay in the gas phase. Well, with DuPont membrane that allows just for the permeability of just the gas into the liquid, you're in essence able to saturate the liquid going into the reactor by using this module. So you put the gas phase on the shell side and liquid on the tube side. It runs through this coil, and in essence, it's not shown here, there's a manifold that's connected to this that enables you to maintain the pressure all the way through. So in essence, you saturate your liquid, and it doesn't have to be hydrogen either. It could be CO, CO2, methane, ethylene, whatever volatile you have that you want to feed into the reaction with your solvent. You can do that through a gas addition module. Okay, so now I'm going to get to a completely different reactor, and this is what I mentioned before, this agitated cell. I held it up before. This cell goes back and forth and agitates within that small. Let me get it out again. Sorry about that. Kind of got ahead of myself. So there are small rings inside of here, and they shake back and forth. So in essence, this becomes the equivalent of one CSTR, if you will, a very small volume that's agitated. Or instead of doing it on a small scale, slightly larger scale is in tubes, and that's also agitated externally. Next slide. So it shows it shaking back and forth. It's a mix. Keep going. And what happens is this unit, if you look on the inside of it, I gotta do a little bit more weightlifting, I think. This panel is on the inside of that sandwich, and this shows the various components where one chamber is connected to the next, to allow the flow to go down. This whole sandwiched item is put inside of a shaping table, And that's how you get the external agitation. No drive shaft, no connection other than to the feeds and outlets, plus also you can see the tubing over here for removing heat. So in essence, what this allows you to do is do a slower reaction with high amount of heat generation at very low throughput and still be plug flow. That doesn't exist in too many places. So that is a very unique and capable design that is now starting to become at least understood, I guess, and prevalent in a lot of different areas. And I mentioned at the table over here, especially in Asia and China, where because there's not as much infrastructure for flow chemistry over there, they're a little bit ahead of the U.S. in that regard because of our inherent batch infrastructure. But we're hopeful that that's going to change. So anyway, this is a lab scale reactor for doing this continuously. Next. And then I mentioned the agitated tubes, and these are along this axis here. Those are tubes that are also agitated and shaken, if you will, externally. Again, no drive shaft, no seals. When I worked in the polypropylene industry, we had a huge issue with titanium trichloride catalyst getting into the seals of the agitations and mixers and actually destroying the seals. That can't happen here because, in essence, you have an external agitation. It might seem counterintuitive to do that, to shake the entire reactor, but to get rid of that seal, to get rid of that agitator, also have plug flow at a very low throughput, that's the benefits that you get from doing it. So again, this opens up a whole new world of chemistry that would not be available if not for these designs. So last but not least, we're going to talk about spinning disk reactors. By the way, is there any questions? I'm kind of on a roll here, so I'm going to see if anybody is. I'm going too fast for you, too slow. Is there anything that you would like me to elaborate? Oh, here we go. Great.
I'll give you a question. With regards to temperature for your co-flow reactor.
For what?
For your co-flow reactor.
Yes.
Front there. With regards to temperature, how uniform is it across the block?
How uniform? Very low delta T. If you want it that way, you could have multiple zones also.
Okay.
You could have cooling and heating. And also, I've seen that there's a paper out from Virginia University where they've actually done pH adjustments by swinging the pH from 2 up to 12 and doing precipitations as well, all within the same block by the counter current of the feed and taking the solids out at the right place.
Okay, so there's no concern about hot spots or cold spots?
No, not with this. No, what happens is there's enough metal there, and you swamp the cooling surface with the coolant at the proper rate. And this company is very good at doing development work with you in order to understand the exotherm to make sure that that doesn't happen.
And then I have another question about your first reactor.
The chip?
Yeah, the chip reactor.
Okay.
What's the average lifespan of that reactor since it's made out of orso paper glass?
10,000 years. I mean, unless you drop it, and it's like 10 minutes.
The concern that I have is if you're putting in reagents in there, like that might be slightly basic, and wind up etching things or something to that effect. You're running this at such a large, you have such a small capillary, and you're putting a tremendous amount of pressure on there. I wonder if there's any slight chance of any kind of interaction with the hydroxyls on that glass.
I'm sure there is, and I'm sure there is some wear of that because of the nature of the glass, but that's in essence what's happening in a batch reactor. Now, granted, the surface area there is much greater than what you would have in a batch reactor, so I really can't talk to that intelligently. I don't have the answer to that. But I'll look it up. I'll get the answer for you, though. Yeah.
And for the shaking reactor?
Yes.
How large can those go in terms of product production?
The largest one that I haven't shown it here is called a rotating tube disc reactor, and that's a RTR, and the volume of that is 100 liters. So it's a fairly significant residence time, and that one works by actually rotating the outside of it, rotating it back and forth, and that's a very extremely large scale. So in essence, all of these companies are set up to work with you in terms of getting you to the small scale, exhaustive understanding of the reactions, exhaustive understanding of what your issues are. Because remember that you're doing it for 3 or 4 items, they've done it hundreds of times, and so in essence, getting the scale up right. And of course, with their credibility is on the line, so they want to make sure that you're successful at the same time. So they're looking at exotherms, solids handling, materials of construction, Hastelloy, glass. I didn't mention it before, but the other company, Chemventive, has their plates are supplied by 3M, and they're made out of silicon carbide, which is the most chemically resistant material and high heat transfer that I'm aware of.
Yeah, maybe I'm by far not a chemical engineer, and maybe I missed something, but what you're talking about here is all about reactions in solution, or does it apply also to particulate systems, slurry or suspension? Because there, the surface area is going to be very much dictated by the particle size. So does this apply to both, or?
Well, it would apply to the ones with the particle size if you had a packed bed. There are cartridges for actually making packed bed reactors and flowing through that. I don't know if that's, but the agitated reactor can also handle slurries with solids that are generated in situ. Now there is one issue that is being worked on aggressively, and that's feeding of solids to these reactors under precise and controlled conditions.
Yeah, because that's a challenge.
Right, but I'll get into the spinning disk reactor in a second. But this one has also been used to, is getting involved with development of nanoparticles as well.
Yeah, that's exactly where I was a little.
Okay, well I haven't got there yet.
Okay, sorry.
No, that's all right. It's a good question. It's a good question. Yeah.
You would just remember to repeat the questions.
All right, I'm sorry. Okay. All right, do you want me to repeat that one? Or?
Just from now on.
Okay, all right. Sorry about that. Thank you. Go ahead. Okay, this is a spinning disk reactor. This is, when you look at it, it looks like a centrifuge, but it's not. It's not making a separation. It's forcing reactants together. And if we start, let me get Norman's pointer so I'm not in front of everybody. If you start with a reactor coming in here from the side, this is a shaft with a disc, and this disc is spinning at 14,000 RPM. And you force fluid up through the middle center portion of this, up into this annular zone with this very small gap that could be as small as 50 microns. And another fluid coming up through an annular space, such that what's happening is you're forcing one fluid through the other at extremely high shear. So in essence, what happens is both fluids are then forced to come together, flow around the disk, come out this side, and then come out through the exit tooth. So this is exit area. So you can adjust the size of this gap, in essence, generating whatever you want for a residence time, put the flows together so that you can have a reaction happening in milliseconds or microseconds, or several seconds if you want, depending upon what you want for a residence time. And if you're going after reactions that are extremely fast with a high heat transfer, this is the way to go. And also, getting back to your question about nanoparticles, this is also a good one for that as well. And this is this design is, as I said, this micrometer can adjust the rotated gap width, and typically they use 100 microns for the size. So, can you back up just a second?
Peter, you could have.
I didn't talk about one of this. Go backwards. Page. Yeah. Go ahead. Sorry.
You could have two immiscible fluids, like in a phase transfer reactor.
Yes.
And that system would work well.
It would work very well with that, because in essence you with the shear levels of this system are way beyond what's in a batch reactor or even in some of the other ones, because in essence you're just mashing these molecules together, which is something that I've never seen in any of the kinetic literature, is what the effective mixing is. People talk about it, but no one, if you look at the kinetic expression in Levenspiel, there's no part of that equation that says the F function of mixing. It says function of concentration, function of temperature, function of other attributes, but not the function of mixing. So that'd be, if someone's interested in doing a PhD thesis, that's a good place to go. Go ahead.
I was going to bring this up later after you went to the spin disk reactor, but I was wondering, there's a whole class of reactions in the literature studied by Professor Bourne, Professor Villermo, that are mixing sensitive.
Okay.
The selectivity is driven in these competitive consecutive or competitive reactions with very different reaction rates,
okay,
or rate constants. The selectivity of the reactions are driven by the intensity of the mixing.
Right.
And what I was going to ask is if any of the systems that you've talked to this point have been studied using those sorts of reactions. Because one fundamental thing about a flow system that you've described so far is it's like I'm running a batch reaction all on board. In other words, I dumped all my reagents together and I'm pushing them down the pipe because the systems you've shown are single injection. So you show great advantages in terms of the heat removal capability and the residence time that you can dial in, no question. But if you have a sensitive system, what goes on as those reagents are mixing in that first length of the reactor can be critical.
Right.
Now, last year, I can't remember who wrote the paper, there was a study using some of the Bourne reactions on spinning disk reactors, and I don't remember the particulars of it, but it is related to the energy dissipation rate. The higher the energy dissipation rate, the better the selectivity. So you'd be going in the right direction that way. I was just wondering if some of the other reactors that you have been characterized using those model reactions.
I can assure you that they have been, just the work hasn't been published. A lot of it is proprietary.
One of the interesting things could be, in terms of marketing these products, is to say, all right, here's the type of relative reaction rates that these particular reactors can go and deliver. Otherwise, then you're pushing yourself into the more intense devices like the spinning disk or other rotor stator type reactors.
Well, that's why you go through the screening experiments with the flow tube reactors. If you have a homogeneous phase, you really find out where you are, what the capabilities are. But in essence, you have to have a sense that the reaction is going to go in a reasonable amount of time. Now, when I say reasonable amount of time, even in the flow tube reactor, you can dial the residence time from having a very small reactor, 2 ml, pumping through a 20 ml per minute, which is going to give you a residence time on the order of 10 seconds, to pumping through a 0.2 of an ml per minute through a 50 ml reactor that's going to give you residence times of hundreds or close to 500 seconds. So in essence, you can screen all those. Getting back to the question about whether or not all of this has been studied and quantified, I think you mentioned, I'm not familiar with that paper. I guess I'm going to look it up. You say the Bourne reaction?
Yeah, we'll exchange cards. I'll send you an email.
Right.
There's some very good references on that. And it might be a nice selling feature for these to talk about the spectrum of these type of reactors could accommodate these sorts of reactions versus going to a more intense device where
the expert
flow doesn't drive your mixing.
The expert in this field that developed the Kinetichem is a gentleman by the name of Robert Tinder, and he's in our group, and he's developed these reactors on a small scale, and I'm sure he's very familiar with that. All right, go ahead. So stop, go back. So anyway, what I wanted to mention about this slide was on the left-hand side here you've got a logarithmic scale of kinetics and mass transfer, and on the x-axis is the energy dissipation rate. And if you look at the various reactors that are out there, we're living in this world down here in the lower left-hand corner, stirred tanks and counter-current packed beds, and technology that I developed with Roman and John was a bubble column, whereas really where the game is played now is way up here at several orders of magnitude higher with a rotating rotor stator spinning disk reactor. Obviously the economics have to support that, but in a lot of these high-valued pharmaceuticals it does. Next. So we went through that. Next. So anyway, this is a published example of that. This is a lithium exchange reaction for exchanging lithium on bromine in a halogenated aromatic. The heat release here is huge, and usually what's happened is this reaction is required and the batch is run at minus 78 degrees C. Here what they did is they ran it through the synthetron spinning disk reactor, got a 98% yield, did it at room temperature. So in essence, that kind of gets to your point that you've got to know what the heat release is, and you've got to know you set the and because of the experience that they've already developed, they know how much heat that they can take out based on some of the other experiments they've done, so they can come pretty close to figuring that out. Now, if the heat release isn't known, the chemical potential is on the moon. I mean, I made one of my projects several years ago was reacting sulfur trioxide, which is a precursor to sulfuric acid. That is a lot of heat release. So I haven't seen that happen in this, but in essence, by the experience that the folks like Robert Tender and Charlotte Wiles and Robert Ash have already put together, they pretty much know where all these are going to fall, and if they don't know that, they're going to work with you to get you to that point. Okay, next. So anyway, I mentioned at the beginning that there's other generalized commercialization review reactions that are in the literature. One thing I will mention is I can't say the name of the pharmaceutical company, but we talked to one very large one, Fortune 50 company, said we are not developing any more reactions that involve batch. It's all continuous. It's all we're doing. And in essence, they're putting a stake in the ground saying, this is the future going forward. So we had an active discussion over here about to what degree flow chemistry is being used out there. And I use the analogy that this is like the world of the PC back in the mid-1980s. You got your 286 PC and 386 PC. You mix and match the different components. Some information, some equipment is available off the shelf. A bunch of us are out running around to computer shows and putting our own systems together. There are people out there building their own reactors and building their own systems, really from scratch, being their own project engineers. So it's a world that still needs to be thrashed out and shaken out, and I expect that to happen over the next 10 to 20 years. That's it. Thank you. And there's more here, but I didn't go into all of it.
Any further questions for Peter?
Yeah. I have a question out of curiosity. When you come and install such a system in a facility, obviously I'm sure you go through training and all of that, but do you have to have some kind of a stamping from OSHA or something of that nature, any regulatory agency that comes and looks at this equipment in terms of safety for the operators?
Well, the question is safety for implementation when you put a system like this in, and what do you have to go through in order to do that? For myself, not for these systems, but this is coming, you have to go through a formal risk management plan. You've got to look at absolutely every attribute, not just what might happen if you get a leak or if programming has a problem, but other things, if an airplane should hit the facility or a tractor trailer should get loose and run through the front of the lobby or something and destroy everything that's in the lab behind that. So you've got to go through that overall evaluation anyway, go through the probabilities and risks of that. That's a somewhat of a tedious procedure, but what happens is I've gone through these, we've had 700 lines on a spreadsheet, and all of a sudden 4 or 5 of them say, well, we didn't think of that. We need another instrument here. We need something else over here. We need another procedure put in, what have you. And that's what that review planning does. So yes, you've got to go through all of that with these systems, but for any chemical system that's using any type of hazardous. Now the other part of your question is on the regulatory, on the GMP side, and that's something else we talked about over here. And that is that for GMP, you've got to have a formal procedure that's unequivocal, that captures all of the process information and doesn't allow, or within 5-9 statistics, any deviation if all of the attributes are followed. The FDA has come out and said unequivocally and published the fact that they're supporting continuous flow chemistry. They want chemical companies to go in this direction. They see the benefits of it, the energy savings that can happen, the improvement in quality, and obviously the economics. Now, has that filtered down to the field level yet? Well, that's where the rubber hits the road. No, it hasn't. So there are individual
so you don't
agents.
Have post-market surveillance.
What?
You don't have post-market surveillance. Post-market surveillance, like after you installed it, surveillance.
Yeah, I believe so. I mean, I'm not familiar with that term. So. But yeah, you'd have that by going through your risk management plan and saying the procedures that you would set up. You're going to calibrate all your instruments. You're going to have an SOP that's detailed and covers all the attributes.
Right, my question was more on the regulatory authority that comes is there such a thing, even like stamping it for safety or not?
What happens is you supply your risk management plan to the authorized regulating authority. That could be a state, that could be a county. In California, it could be an air district. And in essence, you submit that to them and show that you've gone through, and the people that participated in that risk management plan, and they've got to have the appropriate accepted certifications for that as well. Once you've gone through all of that, then in essence they can accept it or reject it. But if they're going to reject it, they've got to give you an answer, and then that answer is something that you go out and figure out a way to fix. Unless you've got a huge hole in the process that makes no sense. I mean, that's something that's I've just never seen that happen. Go ahead.
As a general rule, could you say the yield and purity and continuous flow is better than a batch mode? Well, it's an impossible statement to answer. And there's also an important safety component. I'm working on something that has an purity that's mutagenic, so we're looking at flow chemistry. The downside I see to this, if I understand it correctly, isn't there a limitation to how much mass you can make of any given product? You can't make metric tons this way.
Okay, so the question.
I'm asking about 4 questions here.
That's all right. So let's see. The first question is I forget the first question. I'm sorry. Go ahead. Repeat.
Yes. What would you expect the purity?
Oh, the purity. Okay. So the question is, would the purity be in general? Would you expect the purity to be higher? I'd expect the purity to be much higher because you've characterized the reaction to a much greater degree than you do in batch. In a batch reactor, you've got concentration gradients, you've got heat transfer gradients. You've got situations where you've got the potential for exotherms because you can't get the heat out. So in essence, and also you have the issue of getting a sample out at the right time, if you will. And I've seen all those issues. In the continuous process, because you're not time dependent. Remember the unsteady state aspect of a batch reactor takes you through ranges of concentration, heat transfer, and operations in a plant or on a large scale that are different for every moment in time. Once you set up a continuous system, that dependent variable goes away. It's just gone. So so the issue is you've got to set it up properly. So if you don't set it up properly, then you're going to have much greater impurities. Once it's set up and characterized, then you're off to the races. And I've seen that in much larger continuous processes, not just flow chemistry ones, but the other ones I've worked on in the precious metal industry and developing continuous polypropylene.
But is there a fundamental limit to how much material you can make? You can't make 100 metric tons of acetaminophen or ethyl isocyanate or something like that.
Well, you can make tons of material. You know, that Chemtrix company has a Plantrix unit that makes tons per day of material.
And how big is the equipment relative to what you're showing here?
My understanding is it's probably a 4x4 plate, maybe 10 of those, 6 of those for that scale.
Then.
Yeah, it's scalable and it's contained.
And is it scalable between doing these reactions? It looks like you're almost using a mixture design experiment where you're looking at all these different variables, and then that scales up to the larger.
Right. What you're doing is you're screening at a small scale to get. I mean, my first boss told me about the way the way the Navy hits a ship, right? You shoot too far, too close. Try not to hit it on the third one. You try to guess to be short or long, and then you hit it on your fourth shot. So that's the best I can say. But you're screening unless you already know what the reaction is, and then why go through the exercise because you already know it. What was you had another question here too?
I think you answered.
Okay. Anything else?
So now let's thank Peter for a nice talk, and also John Newport.
Thank you.
Keys to your badges on the table there before you leave.
Is that okay?
That's great.
Was it? I hope so.
So,